Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to use a precise definition of a limit to showcase that a limit does not exist, specifically for this piecewise defined function, which is 1 for x being greater than 0 and -1 for x being less than 0. Graphically, this should make sense because you have something like this, where your graph is disjoint, where you have this discontinuity at 0. So there's this jump. You can see the limit from the right and from the left are not the same, and so therefore the limit should not exist. But how do you use the precise definition of a limit to showcase that this limit does not exist? Well, let's recall the precise definition of a limit. Let me scroll down a little bit. So recall that the limit as x approaches 0 of a function h of x equals L is the kind of the shorthand notation for the following statement. For every single epsilon that somebody gives me, and so let me go ahead and actually point at the upside down capital A for those who are not in my class and just say that means for all or for every. For every single epsilon that somebody hands me, there exists, or in other words, we can find a delta that is positive such that the distance between x and 0 being less than delta will imply that the distance between h and L is less than epsilon. And just as a side note here, that greater than 0 is very important because we cannot allow our x values to become 0. X is approaching 0, but it should never become 0. Okay, that's what the true definition of a limit means. And I'm assuming at this point that you know that definition. That's a prerequisite for this problem. So let's go ahead and showcase that the limit for this function does not exist as x approaches 0. And the way we're going to do that via a proof is we are going to go ahead and assume by contradiction that the limit does exist. So here we go. Assuming that the limit actually does becomes some number L. We don't know what the number is, but we're going to assume that's the case. By the definition of a limit that we've just recalled here, that will imply that any epsilon that somebody hands me, I should be able to find a delta. Okay? So specifically, I can say somebody handed me an epsilon of 1, or an epsilon of 1/2, or an epsilon of whatever number I want in this problem, because I'm saying that this limit exists. So we'll assume that somebody's handed us an epsilon of, it really doesn't matter, let's say of size 1/2. Now for this epsilon, that means that there is a delta to make this definition true. There's a delta such that as long as the distance between x and 0 is less than delta, we know the distance between our function h and L is less than epsilon. Okay, great. So for epsilon equals 1/2, we know we can find a delta so that the distance between x and 0 being less than delta will imply the distance between our function and L is less than that epsilon, which is 1/2. Well, okay, great. Let's clean this up a little bit. This implies that the absolute value of x must be less than delta will imply that the distance between h and L is less than 1/2. Really, I'm just cleaning it up very, very little here. Now, here's the deal. You have two choices for x in this situation, two possibilities for x. Either x is greater than 0 or x is less than 0, right? Because remember, x is approaching 0, but it's not actually equal to 0. In fact, I didn't really write it in there, but just for argument's sake, let me go ahead and write that in there. Now that first notation means the following. If the absolute value of x is greater than 0 but less than delta, that means x could be any number between 0 and delta, right? So pretend as though, just for argument's sake, pretend as though delta is 1. Since the absolute value of x has to be between 0 and 1, and maybe I'll write this off to the side so you can see this argument. So if somebody said I had a number whose absolute value is less than 1, well, then that number could be between 0 and 1, or it could be between -1 and 0. Think about that. -1/2 in absolute value is between 0 and 1, and 1/2 in absolute value is between 0 and 1. So that gives us this inequality grouping here, compound inequality, this guy right here and this guy right here. Okay, so if that's the case, if I know that x is between 0 and delta or between negative delta and 0, I'm going to take it in both cases here. Now remember, we're assuming that epsilon, that somebody walked in and handed us an epsilon of 1/2. It's not a bad assumption because the reality is that the real assumption in this case is that the limit exists. So it has to be true for any epsilon that somebody hands me. I'm just choosing epsilon equals 1/2. This proof would work if you did epsilon equals 1/10 or 1/100th or anything like that. It would be kind of broken if you chose an epsilon equals 1 though, or 2. Okay, so anyway, for x between 0 and delta, we know, or we have, since x is positive, h of x will equal 1. Let me scroll up so you can see. Remember, if x is positive here, then our function value is 1. So we're splitting into two cases, x being positive or x being negative. In the first case, if x is positive, then our function is 1. And so the distance between 1 and L is less than 1/2. That's just stealing this notation here again, because we know we're assuming that the limit is true. Therefore, if x is between the 0 and delta, this limit still has to be true. But now I'm going to go ahead and write that as triple-sided inequality. Remember how absolute values work. The absolute value of something being less than 1/2 means that that something is between -1/2 and +1/2. Let's go ahead and subtract 1 from all three sides. And then let's multiply everything by a negative. Remember, inequality signs flip when you multiply by a negative. So we have this statement, and I have a habit. I like to go from lowest to highest. So let me rewrite that one last time. So 1/2 is less than L is less than 3/2. So in this case, when x is positive, we have that h of x is 1, obviously, because x is positive. Therefore, our limit must be some number between 1/2 and 3/2. So we know now that if this limit exists, which we're assuming it does in this problem, that this L here is between 1/2 and 3/2. Okay, but that statement is true if x is greater than 0. What if x is less than 0? Well, it should still be the case that, let me write this down, if, let's see, negative delta is less than x is less than 0, so x is less than 0, then h of x is -1, again, because going back to the definition of h of x, if x is less than 0, then we know that it's -1. But the reality is we've already shown through logical deduction that L is between the limit that our function is approaching is some number between 1/2 and 3/2. So it shouldn't change here. It should be some number between 1/2 and 3/2. It might tighten up a little bit, but it should be the same kind of, it should be an included range within this. So let's see where this leads us. So again, just building on this, since x is between negative delta and 0, we know the distance between our function, which right now is going to be a -1 and L, should be less than 1/2. So that's what I'm writing in here. The distance between -1 and L is less than 1/2. And again, by the same argument, absolute values being less than some certain number will imply that the argument within the absolute value is between -1/2 and 1/2. Add 1 to all three sides, and this looks pretty good, right? 1/2 is less than -L is less than 3/2. It looks pretty good so far. And multiply everything by the negative. Remember, when you do that, you swap signs. So -1/2, or you swap inequality signs. That's what I meant to say. And I like to write from lowest to largest, so that'll be -3/2 is less than L is less than -1/2. But if you look at these two inequalities, there's a problem. This inequality here tells us as long as our x's are greater than 0 but still less than delta, we totally know what our limit for our function is. Our function is going to limit to some number between 1/2 and 3/2. The next statement says, but if x is less than 0, our limit is going to be between -1/2 and -3/2. And that is not the same exact range. Well, this means that L is positive. Our limit is both simultaneously greater than 0 and less than 0. Now, I don't know about you, but I can't think of any number that's simultaneously greater than 0 and less than 0. Therefore, this is a contradiction. And when you reach a contradiction in a proof, you have to rewind until you find your assumption. Now, all these lines you see here are logical arguments that stem from one single assumption. The single assumption we've made is this guy right here. You assume that the limit of your function is equal to L. The reality is that that's the only assumption we have, thus, this assumption must be wrong. In other words, the limit for our function cannot become some number, L. That is, it must not exist. So let me write that down. Hence, the limit as x approaches 0 of our function cannot exist. And then that ends the proof, QED.